For most of human history, the concept of a true and absolute void was not merely an abstract idea, but a philosophical impossibility. This deep-seated aversion to emptiness, known as horror vacuo, was most famously articulated by Aristotle, who declared that nature abhors a vacuum. To the ancient Greek mind, empty space was a logical contradiction. Motion and interaction required a medium, a plenum or fullness that filled all of space. Just as a fish needs water to swim, objects in the universe needed a substance through which to move and exert force. The idea of action occurring across sheer nothingness was incomprehensible. This philosophical foundation persisted for millennia, shaping how thinkers understood the physical world. Even during the scientific revolution, luminaries like René Descartes adhered to this principle, envisioning a universe filled with subtle, invisible fluids that transmitted forces through direct contact. To them, the notion of a magnet pulling on a piece of iron across empty space was as absurd as a ship sailing without an ocean. This ingrained belief in a cosmic medium set the stage for one of the most intriguing chapters in the history of science: the hunt for the luminiferous ether. The puzzle deepened with the growing understanding of light. By the 17th century, a fierce debate raged over whether light was composed of particles, as Isaac Newton argued, or whether it behaved as a wave, as Christian Huygens proposed. Gradually, evidence mounted in favor of the wave theory. Light exhibited interference, creating patterns of light in dark bands, and diffraction, bending around obstacles, phenomena that were hallmarks of wave behavior. But this conclusion brought with it a profound dilemma, one that echoed the ancient unease with the void. Waves by their very nature require a medium to propagate. Sound waves travel through air, water waves through water. Remove the medium and the wave vanishes. A wave is not an entity in itself, but a disturbance moving through a substance. If light was a wave, what was the substance it was moving through? Starlight traversed unimaginable distances across the vacuum of space to reach Earth. It was clearly a wave, yet it seemed to be traveling through nothingness. This was scientifically and philosophically untenable for 19th century physicists. The idea that light waves could propagate through sheer emptiness was as irrational as sound traveling through a vacuum. There had to be something, an invisible, intangible, and universal medium that filled the cosmos and served as the stage for light's performance. This medium, they reasoned, must be unlike any known substance, massless, frictionless, perfectly transparent, and elastic enough to vibrate at the extraordinarily high frequencies of light. It had to permeate everything, from the vast expanses between galaxies to the microscopic spaces between atoms. Thus, the concept of the luminiferous ether was born, a ghostly medium postulated to solve the puzzle of light's journey through the void. It was an elegant solution to an ancient problem, a necessary dancer for the wave of light. Yet this very ghost would soon lead scientists on a path to a revolutionary discovery, one that would ultimately dismantle the idea of the ether itself and redefine our understanding of space, time, and the very fabric of the universe. The philosophical aversion to the void had persisted for millennia, but it was in the 19th century that this abstract unease crystallized into a formal, scientific entity. The catalyst for this transformation was the overwhelming experimental evidence for the wave theory of light, championed by a new generation of physicists who needed a physical mechanism to make their mathematics tangible. The concept of the luminiferous ether was no longer just a philosophical preference. It became a theoretical necessity, a cornerstone of classical physics whose properties were meticulously, if bewilderingly, defined. The pivotal figure in this formalization was the French physicist Augustin-Jean Fresnel. Building on the earlier wave ideas of Christian Huygens, Fresnel provided a comprehensive mathematical treatment of light as a wave phenomenon. His equations brilliantly predicted and explained a host of optical effects, from the intricate interference patterns created by double slits to the complex refraction of light through crystals. Fresnel's work was a triumph of theoretical physics, but it came with an inescapable implication. His equations described a transverse wave, a wave that vibrates perpendicular to its direction of travel, like a ripple on a shaken rope. This was critically different from a longitudinal wave, like sound, which vibrates parallel to its direction of travel, like a compressed slinky. This distinction was everything. Physicists knew that a transverse wave could only propagate through a solid, Liquids and gases can support longitudinal waves, the push and pull of pressure, but they cannot sustain the side-to-side shear forces of a transverse wave. If light was a transverse wave, as Fresnel's irrefutable mathematics showed, then the medium carrying it, the ether, could not be a tenuous gas or fluid. It had to be an elastic solid. This was the first and most startling property assigned to the ether. It was a solid that filled all of space, but this immediately created a paradox of monumental proportions. How could the universe be filled with an all-pervading solid that offered no detectable resistance to the motion of planets, comets, or even falling apples? The ether had to possess a set of almost magical, mutually exclusive properties. It needed to be incredibly rigid to support the extremely high frequency of light vibrations, far more rigid than steel, to account for the immense speed of light. Yet it simultaneously had to be infinitely fluid and frictionless, allowing celestial bodies to glide through it for eons without any loss of momentum. It had to be massless and perfectly transparent, leaving no trace of its existence except for its role in carrying light waves. Scientists reconciled these bizarre requirements by imagining the ether as an ideal massless solid. It was not a solid made of atoms in the conventional sense, but a continuous, perfectly elastic medium. It could transmit shear waves due to its inherent elasticity, but because it had no mass or internal friction, it could not impart any drag or resistance to matter moving through it. Matter was thought to be largely transparent to the ether, with the tiny particles of atoms simply moving through the dense, ghostly fabric of space without disturbing it on a large scale. This was the prevailing, if deeply strange, picture. Every corner of the universe was filled with an invisible, intangible, massless, perfectly rigid, yet perfectly frictionless solid. With this conceptual framework in place, the ether became the established stage for all of physics. It was the absolute rest frame of the universe. Just as sound waves travel at a fixed speed relative to the air, light waves were now understood to travel at a fixed speed, crs, relative to this stationary ether. This led to a powerful and testable prediction. If the ether was stationary and the Earth was moving through it as it orbited the Sun, then the Earth should be experiencing a constant ether wind. Just as a cyclist feels a headwind even on a still day, the motion of the Earth through this stationary medium should create a detectable drift against the flow of the ether. The luminiferous ether was thus born not from wild speculation, but from the rigorous demands of the best physical theory of the age. It was a masterpiece of classical reasoning, an elegant solution that reconciled wave optics with a mechanistic universe. It provided a physical reality for Fresnel's beautiful mathematics and banished the specter of action at a distance. For a time it brought order and comfort, filling the terrifying void with a substance that, however peculiar, obeyed known physical laws. The stage was set, the actor, light, was understood, and the medium, the ether, was defined. All that remained was to detect this ghostly presence, to feel the whisper of the ether wind, and confirm the material nature of space itself. This confident expectation would soon set the stage for one of the most famous failed experiments in scientific history. For a glorious period in the 19th century, the luminiferous ether was not a debated hypothesis. It was an established fact of the universe, a triumphant theory that elegantly unified and explained the burgeoning science of optics. With the ether as its foundation, the wave theory of light achieved a level of predictive power and conceptual beauty that solidified its dominance. This was the ether's golden age, a time when it moved from a necessary postulate to a celebrated cornerstone of classical physics, providing intuitive and mathematically rigorous explanations for phenomena that had puzzled scientists for centuries. The most profound success of the ether theory lay in its elegant explanation of reflection and refraction. Why does a beam of light bounce off a mirror at a perfect angle, or bend when entering water? Fresnel's equations, which treated light as a transverse wave propagating through the ether, provided the answer. The ether itself was thought to permeate all matter, but its properties, specifically its density and elasticity, were modified by the presence of transparent materials like glass or water. When a light wave, a vibration in the universal ether, encountered a new medium, the change in the ether's properties at the interface caused part of the wave to be reflected back and part to be transmitted inward. The change in speed as the wave entered the denser optical medium was what caused the beam to bend, a phenomenon known as refraction. The mathematics predicted the exact angles with stunning precision, turning the qualitative observations of optics into a quantitative science. The ether was the stage, and the changing properties of this stage from air to glass directed the ballet of light with perfect, predictable grace. Furthermore, the ether provided a beautifully mechanical model for the very essence of light's wave nature. The complex phenomena of interference and diffraction, which had been major sticking points for Newton's corpuscular theory, became intuitively clear. Thomas Young's famous double-slit experiment, which produced alternating bands of light and darkness, was irrefutable evidence of wave behavior. With the ether, one could visualize this. The peaks and troughs of light waves propagating through the elastic ether would arrive at the screen. Where two peaks met, they would constructively interfere, creating a bright band. Where a peak met a trough, they would cancel each other out, creating darkness. This was not some abstract mathematical trick. It was the expected behavior of real waves in a real physical medium. Diffraction, the bending of light around obstacles, could likewise be understood as the ether waves spreading out after passing an edge, just as water waves bend around a rock in a pond. The power of the ether framework extended to the newly unified field of electromagnetism. When James Clerk Maxwell derived his famous equations, he did so by considering the mechanics of vortices and idle wheels within this ethereal medium. The ether was not just for light. It was the substrate for all electric and magnetic phenomena. Maxwell's work showed that light itself was an electromagnetic wave, a coupled oscillation of electric and magnetic fields propagating through the ether. This was perhaps the ultimate triumph, the unification of light, electricity, and magnetism into a single elegant theory, all rooted in the dynamics of the ether. The speed of light, AgCal, could now be calculated from purely electrical and magnetic constants, and its value matched direct measurements. This was seen as a spectacular validation of the entire theoretical edifice. The ether was not just a convenient idea, it was the fundamental entity from which the constants of the universe could be derived. During this golden age, the ether's existence was as unquestioned as the existence of atoms is today. It was the absolute stationary frame of reference against which all motion in the universe could be measured. Textbooks presented it as fact, and leading physicists built their careers upon its foundation. The universe felt understood. It was a continuous mechanical system. Every action had a direct local cause transmitted through a physical medium. The ether banished the spooky notion of action at a distance, ensuring that physics remained rational and deterministic. It was a comforting picture, a universe filled with a subtle, intelligent substance that guided light with perfect fidelity, explained the colors of soap bubbles, and connected the forces of nature into a coherent whole. For a few decades, it seemed that the ancient dream of a complete and mechanical understanding of the cosmos was within reach, all thanks to the invisible, frictionless, elastic solid that filled the void, the luminiferous ether. The triumph of the ether theory was so complete that for a time, its sheer explanatory power overshadowed a growing, nagging problem. The more physicists tried to define this invisible medium, the more they were forced to endow it with a set of properties so mutually exclusive, so logically contradictory, that the concept began to strain under its own impossible weight. The ether, in order to fulfill all the roles demanded of it, had to be a substance unlike any other in the universe, a ghost with the strength of a titan and the subtlety of a phantom. The first and most demanding requirement was its rigidity. The speed of a wave through any medium is determined by that medium's density and its rigidity, or elasticity. Light waves are transverse, and as we've established, transverse waves can only propagate through solids. Furthermore, light travels at an astonishingly high speed, approximately 300,000 kilometers per second. To account for this, the ether had to be incredibly, almost unimaginably rigid. Physicists calculated that its elasticity had to be far greater than that of steel. Imagine a substance so firm that a vibration in one part of the galaxy could be transmitted to the other side in a matter of seconds. This was the first pillar of the ether's identity, a cosmic solid, a scaffold of unimaginable strength that filled all of space. Yet this presented an immediate and obvious paradox. If the universe was filled with a solid more rigid than steel, how could the planets, moons, and comets move through it so freely? Astronomers had meticulously tracked the orbits of celestial bodies for centuries. Their motions were precise, predictable, and showed no signs of slowing down. There was no evidence of any frictional drag, no loss of orbital energy that would be expected if they were plowing through an immensely rigid solid. The ether, therefore, had to possess a second contradictory property. It had to offer zero resistance to matter. It had to be a frictionless superfluid, allowing Earth and every other celestial body to glide through it as if it weren't there. Physicists attempted to reconcile these opposing traits through increasingly complex models. Perhaps the ether was a strange, quasi-solid state of matter. Some, like George Stokes, proposed that the ether might behave like a rare type of substance, such as pitch or sealing wax. These materials are rigid enough to shatter when struck with a hammer, yet soft and fluid enough to flow over long periods of time. Perhaps the ether was like this, rigid enough to snap back into place at the high frequencies of light, yet fluid enough to allow planets to pass through it over astronomical timescales without noticeable resistance. Another theory suggested that ordinary matter was largely transparent to the ether. Just as a porous sponge allows water to flow through its gaps, perhaps the atoms of planets and stars were so diffuse that the ether simply flowed through them without significant interaction. In this view, the ether and matter coexisted in the same space, barely aware of each other's presence, with the ether only interacting with matter during the specific process of light emission and absorption. But even these creative solutions led to further complications. If the ether was dragged along by moving bodies, as Stokes's model suggested, it should have affected the observed properties of starlight in specific ways. If it was completely stationary and matter passed through it unimpeded, that too had measurable consequences. The attempts to patch the theory only revealed more cracks. The ether had to be massless, yet capable of storing immense energy in its vibrations. It had to be perfectly transparent, yet the very medium of vision. It had to be continuous, yet not disrupt the discrete nature of atoms. These bizarre properties were the first deep-seated cracks in the foundation of classical physics. While the ether was a brilliant conceptual tool for explaining optical phenomena, its physical reality was becoming philosophically untenable. A substance that was both harder than diamond and more yielding than air, that was everywhere but could not be felt or weighed, was starting to look less like a scientific discovery and more like a metaphysical contrivance. It was a ghost invented to do a job, but the job description required the ghost to be in two places at once, to be both tangible and intangible, to be a solid and a void simultaneously. The golden age of the ether was thus a period of both supreme confidence and underlying anxiety. The theory worked magnificently in practice, but its core was rotting from within with logical contradictions. The scientific community was acutely aware of this problem. It was an elegant solution that was, upon closer inspection, too elegant to be true. The stage was now set for a direct confrontation. If the ether was a real physical substance, this universal stationary solid, then its presence should be detectable in a laboratory on a moving Earth. The time for theoretical hand-waving was over. The hunt for the ghost was about to begin, and it would lead to one of the most famous non-results in the history of science. With the luminiferous ether established as a cornerstone of physics, a clear and testable prediction emerged, one that would bring the abstract concept crashing into the tangible world of experimental measurement. If the ether was a real stationary medium that filled all of space, then the Earth was not a privileged observer at rest. It was a moving platform, hurtling at a tremendous speed of about 30 kilometers per second around the sun. And just as a cyclist racing down a still road feels a strong headwind, the Earth in its orbital motion should be plunging through this stationary ether, creating a detectable ether wind. This was not a minor side effect. It was a central, inescapable consequence of the theory. The entire framework of wave mechanics depended on it. The speed of light, was understood to be its speed relative to the ether. Therefore, for an observer on Earth moving through the ether, the measured speed of light should depend on the direction of the light beam relative to this ether wind. Imagine swimming in a river. If you swim directly against the current, your speed relative to the riverbank is slower than your swimming speed. If you swim with the current, it is faster, and if you swim across the current, your path is bent, and your effective speed is different yet again. According to this logic, a beam of light sent in the same direction as the Earth's motion, swimming with the current of the ether wind, should be measured to travel at a speed of c-, the Earth's orbital velocity. A beam sent in the exact opposite direction, against the current, should be measured at c+, the Earth's velocity. A beam sent perpendicular to the wind would have a slightly different speed as well, its path subtly deflected by the ethereal flow. This variation was not expected to be large. The Earth's orbital speed is only about 0.01% of the speed of light, but it was well within the precision of late 19th century instrumentation to detect. This simple, elegant analogy created a clear experimental mission. Build a device sensitive enough to measure these tiny differences in the speed of light caused by the Earth's motion through the ether. The detection of this ether wind would be the final, definitive proof that the luminiferous ether was a physical reality. It would confirm that space was not empty but filled with a substantial, though subtle, medium. It would establish the ether as the absolute frame of reference for the entire universe, the backdrop against which all true motion could be measured. The challenge captivated some of the finest experimental minds of the era. How does one measure the speed of something as unfathomably fast as light with the precision needed to detect a 0.01% variation? The answer lay not in timing a single beam of light over a known distance, but in using the wave nature of light itself to create an exquisitely sensitive comparator. The proposed method was interference. The plan was to split a single beam of light into two parts, send them on perpendicular journeys of equal length, and then reunite them. If the two beams traveled at the same speed, their light waves would recombine in sync, creating a bright interference pattern. But if the ether wind was blowing, it would affect the two beams differently. The beam traveling parallel to the wind would be slowed down or sped up relative to the beam traveling across the wind. When the two beams were brought back together, their light waves would be slightly out of phase. The peaks of one wave would no longer perfectly align with the peaks of the other. This misalignment would cause the interference pattern of light and dark bands to shift, a detectable, measurable change. All one had to do was set up such an instrument, known as an interferometer, and rotate it. As the apparatus turned, the orientation of the two light paths relative to the hypothesized ether wind would change. The beam that was once parallel to the wind would become perpendicular and vice versa. This rotation should cause a continuous rhythmic shift in the interference fringes, a direct visual signature of the Earth sailing through the cosmic medium. The experiment seemed straightforward in principle. It was a race against the ether wind, a race that pitted the most robust theory of the age against the cold, hard data of the laboratory. The scientific community held its breath, confident that the final piece of the puzzle was about to be snapped into place, confirming the material nature of space itself. The stage was set for one of the most crucial experiments in history, an experiment that would not yield the result anyone expected. The theoretical stage was set. The ether wind had to be blowing. The only task left was to detect it, and the man for the job was Albert A. Michelson, an experimental physicist of almost superhuman ingenuity. His tool, which he would later refine with chemist Edward Morley, was the interferometer, a device of such exquisite sensitivity that it could, in theory, measure the faint whisper of the Earth's motion through the cosmic medium. Its design was a masterpiece of optical precision, a ballet of light and mirrors engineered to reveal the secrets of the universe. The core principle was interference, but the implementation was breathtaking. Michelson's apparatus was designed to split a single beam of monochromatic light and race the two halves against each other. The entire experiment was mounted on a massive solid sandstone slab, which was then floated in a basin of mercury. This was a critical innovation. Mercury provided a nearly frictionless bearing, allowing the entire apparatus to be rotated smoothly and steadily. If the ether wind existed, rotating the device would change the relative orientation of the light paths to the wind, which should cause a shift in the interference pattern. The mercury bath eliminated any vibrations or strains that could mimic this effect, ensuring that any observed shift would be due to the ether itself. The journey of the light began at a single source. This beam was directed onto a beam splitter, a pane of glass half silvered on one side so that it would reflect half the light and allow the other half to pass through. This single act created the two rival beams. One beam, the transmitted beam, traveled straight through the splitter, hitting a mirror at the end of a carefully calibrated path. This was the longitudinal arm. Aligned, the scientists hoped, parallel to the direction of the Earth's motion and the presumed ether wind. The second beam, the reflected beam, bounced off the beam splitter at a perfect 90-degree angle, traveling along the transverse arm, perpendicular to the supposed wind. Each beam, after its outbound journey, hit its respective mirror and was reflected directly back to the beam splitter. Here was the moment of truth. Upon returning, part of the longitudinal beam would be reflected by the beam splitter, and part of the transverse beam would be transmitted through it. These two returning halves were now reunited and coaxially combined, sent together into a telescope for observation. If the ether was stationary and the Earth was moving through it, the two beams should have taken different times to complete their round trips. The logic was impeccable. The beam traveling along the arm parallel to the ether wind would be like a swimmer going upstream and then downstream. Its total time would be slightly longer than if the ether were still. The beam traveling across the ether wind would be like a swimmer crossing a river. Its path would be slightly diagonal to compensate for the current, also resulting in a different travel time. The difference was minuscule, but it was calculable. When these two beams, having experienced these slightly different journey times, were recombined, their light waves would be out of phase. Where they had started in perfect sync, they would now return with one slightly ahead of the other. This would cause the waves to interfere, constructively where peaks met peaks, destructively where peaks met troughs. The observer looking through the telescope would see a pattern of stationary, parallel interference fringes, bright bands of constructive interference and dark bands of destructive interference. The critical test was to rotate the entire apparatus on its mercury bearing. As it turned, the arm that was once parallel to the ether wind would become perpendicular and vice versa. This would swap the expected delay from one beam to the other. This swap should cause the interference fringes to shift. The entire pattern of light and dark bands would be seen to drift sideways in the telescope's view. The magnitude of this fringe shift was predicted to be about 0.4 of the width between fringes, a small but definitively observable amount for an instrument of this precision. Michelson had already performed a preliminary version of this experiment in 1881, with ambiguous results. The 1887 experiment with Morley was a monumental effort to remove all doubt. They extended the optical path by using multiple reflections, effectively creating an arm length of about 11 meters. The stone slab was massive and stable. The mirrors were exquisitely aligned, and the mercury bath allowed for vibration-free rotation. Every conceivable source of error was considered and minimized. The Michelson-Morley interferometer was the most sophisticated device ever built to measure the properties of nothingness. It was a machine designed to feel the breath of the universe. All that remained was to turn it on, rotate it, and watch the fringes dance to the rhythm of the ether wind. In the quiet of their Cleveland laboratory, Albert Michelson and Edward Morley began their meticulous work. They calibrated their exquisite interferometer, ensured its flawless rotation on its bed of mercury, and peered into the eyepiece, expecting to witness history. They were poised to see the rhythmic telltale drift of the interference fringes, the undeniable signature of the Earth gliding through the cosmic ether. They rotated the apparatus, watching, waiting for the universe to reveal its hidden fabric. They saw nothing. The fringes remained stubbornly, impossibly stationary. There was no shift, no drift, no whisper of a wind. The result was not just a small effect. It was a definitive null. The ether wind, which should have been blowing at a brisk 30 kilometers per second, was undetectable. The most sensitive instrument ever designed to find the ether had found precisely nothing. The initial reaction within the scientific community was not immediate acceptance, but profound disbelief and a concerted effort to explain the result away. A null result of this magnitude was so disruptive to the established paradigm that it was considered more likely that the experiment was flawed or that there was a misunderstanding than that the foundational concept of the ether was wrong. The ether was not just a theory, it was the stage upon which all of physics was performed. To declare it non-existent was to declare the play impossible. Thus began a period of what philosophers of science call ad hoc hypotheses, modifications to the original theory designed solely to save it from a contradictory observation. The most prominent of these was the ether drag hypothesis. Perhaps some suggested the ether was not perfectly stationary. Maybe it was partially dragged along by the Earth, much like the Earth's atmosphere is. If the ether in the immediate vicinity of the Earth was moving with it, then there would be no relative wind to detect in a laboratory on its surface. This idea was appealing but problematic. It conflicted with the observed aberration of starlight, a well-documented effect where the position of stars appears to shift slightly due to Earth's motion, an effect that only made sense if the ether was not being dragged along. A more radical and ingenious rescue attempt came from two physicists working independently, George Fitzgerald in Ireland and Hendrik Lorentz in the Netherlands. They proposed a truly bizarre fix. What if the null result was not because the ether wind wasn't there, but because the instrument used to measure it was physically affected by its motion through the ether? Fitzgerald suggested that any object moving through the ether would experience a contraction in its length in the direction of motion. Lorentz provided a more detailed mathematical framework for this, showing how the intermolecular forces within the stone slab and the metal arms of the interferometer would be affected by the ether, causing them to physically shrink by just the right amount to exactly cancel out the expected fringe shift. This Lorentz-Fitzgerald contraction was a brilliant, if desperate, piece of theoretical patchwork. It precisely accounted for the null result. The reason Michelson and Morley saw no effect was that the arm of their interferometer pointed into the ether wind had shrunk, perfectly compensating for the delay the light beam should have experienced. The proposal was both elegant and deeply unsettling. It introduced a strange, unobservable physical effect whose sole purpose was to make the ether undetectable, preserving its existence in theory while banishing it from experimental reach. It was a ghost that could influence matter but could never be seen or felt. For nearly 2 decades, this was the uneasy status quo. The Michelson-Morley experiment was respected but not considered a death blow. The ether, though now hidden behind the clever mathematics of Lorentz and Fitzgerald, remained the foundation of physics. The null result was a major anomaly, a cloud on the horizon but not yet a storm that would wash the old world away. It was a great disappointment because it failed to deliver the expected confirmation. But the scientific community, deeply invested in the ether paradigm, was not yet ready to abandon its cornerstone. They chose to live with a complex, patched-up theory, rather than face the terrifying void of a universe without an ether. The stage was set for a revolution, but it would require a lone patent clerk in Switzerland to look at the same data and ask not how to save the ether, but what if the ether was never there at all? The stark null result from the Michelson-Morley experiment sent a tremor through the foundations of physics. But a well-established paradigm does not fall easily. The initial reaction was not to dismantle the magnificent edifice of the ether, but to shore up its walls against this unexpected assault. The first and most intuitive line of defense was a concept known as the ether drag hypothesis. It was an attempt to explain the perplexing silence by suggesting that the ether was not a stationary medium, but one that was intimately entwined with the Earth itself. The logic was appealingly simple. We know the Earth's atmosphere is dragged along with it. We don't experience a perpetual hurricane-force wind as the planet spins and orbits. Perhaps the ether behaved similarly. If the ether in the immediate vicinity of the Earth was not stationary, but was partially or fully entrained by our planet's motion, then an experiment conducted on its surface would, by definition, detect no ether wind. The laboratory, the interferometer, and the surrounding ether would all be at rest relative to one another. The null result was not a failure. It was exactly what one should expect if the ether was a local, co-moving atmosphere. This idea had a distinguished pedigree. The great French physicist Augustin Jean Fresnel had actually proposed a partial ether drag hypothesis decades earlier to explain a different phenomenon, the aberration of starlight. He suggested that transparent bodies like glass or water would drag the ether within them with a specific, calculable fraction of their velocity. This Fresnel drag coefficient successfully explained why light passing through a moving prism was not left behind. Proponents of the drag hypothesis now extended this idea from small pieces of glass to the entire planet. Perhaps the massive Earth dragged a boundary layer of ether with it, creating a calm local pocket within the greater, stationary cosmic ether. However, this comforting solution immediately ran into a formidable and well-established observational wall, the very same aberration of starlight that Fresnel had sought to explain. This phenomenon, discovered by James Bradley in 1725, is the apparent shift in the position of stars due to the Earth's orbital motion. It is analogous to how raindrops falling straight down appear to slant towards the windshield of a moving car. The angle of this stellar aberration had been meticulously measured for over a century. Its value was precise and consistent. The existence of stellar aberration was powerful, direct evidence that the ether was not being fully dragged by the Earth. If it were, the situation would be like the raindrops being carried along inside the car. They would fall straight down with no apparent slant. An astronomer on a fully ether-dragging Earth would point her telescope directly at a star's true position. But this is not what happens. The telescope must be tilted slightly, proving that the Earth is moving through a medium that is not moving with it. The starlight is like the rain and the Earth is the moving car. The aberration was the telltale slant, proving the ether wind was blowing, even if Michelson and Morley couldn't feel it in their basement. This left proponents with an awkward hybrid model. They had to propose that the ether was mostly stationary to allow for stellar aberration, but somehow partially dragged in the immediate vicinity of the Earth to explain the Michelson-Morley null result. This created a model of baffling complexity. How thick was this boundary layer? How did the transition between the stationary cosmic ether and the dragged terrestrial ether work? Why did it affect light from distant stars one way, but not the light in Michelson's interferometer? Other, more exotic clinging theories emerged. Perhaps the ether was not a fluid but a granular solid, and matter slipped through its lattice structure without disturbing it. Or perhaps the emission theory of light was correct after all, and light particles simply inherited the velocity of their source, making the ether superfluous. But this latter idea conflicted with the well-understood wave nature of light and other astronomical observations. The ether drag hypothesis and its cousins represented a period of profound scientific unease. They were not elegant predictive theories but reactive ad hoc fixes. Their primary virtue was their ability to preserve the cherished ether against a single, devastating experimental result. They were epicycles for the 19th century, complex additions to a dying model, designed to explain away an anomaly rather than lead to new discoveries. The air was thick with intellectual desperation. The scientific community was clinging to the ghost of the ether, endowing it with ever more convoluted and contradictory properties to keep it alive. The stage was set for a more brutal, but ultimately more liberating, solution: the idea that the ghost was never there to begin with, and that the null result was not a puzzle to be solved, but a fundamental clue about the true nature of space and time. While many physicists were trying to explain the Michelson-Morley null result by modifying the ether, one Irish professor, George Francis Fitzgerald, dared to consider a far more radical possibility. Perhaps the problem was not with the medium, but with the matter moving through it. In 1889, he proposed a solution that was as elegant as it was bizarre, an idea that seemed to be plucked from the realm of science fiction. Fitzgerald suggested that all physical objects physically contract in their direction of motion through the ether. The logic, once one accepted the shocking premise, was mathematically straightforward. The Michelson-Morley experiment was designed to detect a difference in the time it took light to travel along two perpendicular paths. The calculation showed that the beam traveling parallel to the ether wind should be slightly slower on its round trip than the beam traveling across it. This time difference was what should have caused the interference fringes to shift. Fitzgerald's brilliant, desperate insight was to ask, what if that time difference didn't exist? Not because the ether wind wasn't blowing, but because the instrument itself changed its shape in just the right way to perfectly compensate for it. He proposed that the pressure of moving through the stationary ether would cause the bonds between the atoms in a solid object to change, leading to a minute compression in the direction of motion. The arm of the interferometer pointed directly into the ether wind would contract. The amount of this contraction was not arbitrary. Fitzgerald calculated that it would be by a factor of the square root of 1v2c2, where v is the velocity through the ether and c is the speed of light. When he plugged in the numbers for the Earth's orbital velocity, he found something astonishing. The contraction would be exactly the right amount to shorten the parallel arm, just enough so that the light beam, fighting against the ether wind, would take precisely the same time to complete its round trip as the beam traveling across the wind. The two times would be perfectly equalized. The fringes would not shift. The null result was not a failure. It was a precise confirmation of a new physical law. The implications were staggering. It meant that the very fabric of the universe conspired to hide the state of absolute motion. It was a principle of cosmic compensation. The faster you moved through the ether, the more you would shrink along your direction of travel, ensuring you could never measure your own velocity through the fundamental medium of space. The yardstick you would use to measure the effect would itself be shrinking, nullifying the measurement. It was a perfectly designed, self-censoring universe. Unsurprisingly, the proposal was met with a mixture of awe and deep skepticism. On one hand, it was a beautifully precise and quantitative solution to the most vexing problem in physics. It saved the ether without requiring complex drag hypotheses. On the other hand, it seemed like a contrivance, an ad hoc fix invented for the sole purpose of explaining away an inconvenient experiment. Critics pointed out that the contraction was, by its very nature, undetectable. If everything contracted, including our measuring rods and our own bodies, how could we ever prove it was happening? It was a ghost of a theory explaining one ghostly result with another. Furthermore, the mechanism was obscure. Fitzgerald suggested it might be related to the interaction of the electromagnetic forces, which hold atoms together, with the ether. A moving magnetic field was known to affect electric charges. Perhaps the motion of the entire object through the universal ether modified the intermolecular forces, causing a compression. But this was a hand-waving explanation, lacking the rigor of a full dynamical theory. Despite the skepticism, Fitzgerald's idea, which was independently and more rigorously derived by the Dutch physicist Hendrik Lorentz, became known as the Lorentz-Fitzgerald contraction. For over a decade, it stood as the most promising, if unsettling, explanation for the Michelson-Morley result. It was a holding pattern, a brilliant and strange compromise that allowed physicists to cling to the ether while acknowledging the bizarre, relativistic-like behavior of matter. Fitzgerald's contraction was the first clear glimmer of a truth far stranger than anyone had imagined. It was a bridge between the classical ether-filled universe and a new relativistic one. He had correctly identified the mathematical relationship that would govern the universe, but he had interpreted it within the old framework. He saw the contraction as a physical compression caused by motion through a medium, a dynamical effect. It would take a young patent clerk in Switzerland to realize that Fitzgerald had the math right, but the meaning wrong. The contraction wasn't something that happened to objects moving through an ether. It was a fundamental property of space and time itself. Fitzgerald had discovered a profound symptom of a deeper disease, and in doing so, he inadvertently wrote the first prescription for the theory of relativity. While George Fitzgerald had launched the radical idea of length contraction as a speculative salvage operation, it was the Dutch physicist Hendrik Lorentz who became its master architect. Working independently and with greater mathematical rigor, Lorentz didn't just propose a contraction, he built an entire theoretical framework to support it. His life's work was a heroic, systematic, and ultimately rearguard action to preserve the ether by endowing matter with a suite of bizarre, compensatory properties. He was trying to save classical physics from itself, and in the process, he accidentally derived the very mathematics that would make its replacement possible. Lorentz's approach was more fundamental than Fitzgerald's. He started from a firm belief in a stationary, electromagnetic ether, and aimed to understand how moving charged particles, which he believed constituted all matter, would interact with it. Using the sophisticated framework of James Clerk Maxwell's equations, he sought to discover the mathematical transformations that would allow the laws of electromagnetism to remain unchanged for a moving observer. This was the critical challenge. If the ether was the absolute rest frame, why did electromagnetic phenomena seem to obey the same laws for observers in uniform motion? This principle, known as relativity, was experimentally suggested but theoretically perplexing. Lorentz's solution was a set of equations that now bear his name, the Lorentz transformations. These were not merely a restatement of Fitzgerald's contraction. They were a comprehensive set of rules that linked space and time coordinates between a stationary ether frame and a frame moving through it. The transformations revealed that the Fitzgerald contraction was not a standalone oddity, but one part of a complex interrelationship. According to Lorentz's math for an object moving through the ether, Its length would indeed contract in the direction of motion by the now familiar factor 1 v to c2, 2. Its time would slow down. Moving clocks would tick more slowly than stationary clocks in the ether, a phenomenon known as local time dilation. Its mass would appear to increase with its velocity. These were not physical effects in the dynamical sense, but were instead the consequences of the way the moving observer's measuring tools, rods, clocks interacted with the ether, corrupting their ability to make a true measurement. The local time was a mathematical fiction, a convenient variable that helped the equations work out, not something Lorentz believed was physically real. The power of the Lorentz transformations was breathtaking. They could perfectly explain the null result of the Michelson-Morley experiment. The contraction of the apparatus and the slowing of its clocks in motion would conspire to completely hide any evidence of the Earth's motion through the ether. They also elegantly accounted for other puzzling phenomena. Lorentz and his colleague, the physicist Peter Zeeman, conducted precise experiments demonstrating how magnetic fields could affect the light emitted by atoms, work for which they received the 1902 Nobel Prize. This provided a plausible, though highly complex, mechanism for the contraction. The motion through the ether could subtly alter the electromagnetic forces binding atoms together, causing the compression Fitzgerald had postulated. Yet, for all its mathematical brilliance, Lorentz's theory was philosophically cumbersome. It preserved the ether as a privileged state of absolute rest, but it then had to explain why this absolute state was forever and fundamentally undetectable. The universe, in his view, was filled with a cosmic conspiracy. Every attempt to measure one's motion through the ether would be foiled by the very nature of matter, which would contract and have its time distorted in just the right way to hide the truth. The ether became a ghost that pulled all the strings of reality, but could never appear on stage. Lorentz had, in essence, constructed a perfect mathematical description of a universe that looked relativistic without actually being relativistic. He had all the right answers, but for what would soon be seen as the wrong reasons. His transformations correctly described how space and time coordinates mixed, but he interpreted this mixing as an artifact of our imperfect, matter-based measurement tools operating within a classical, absolute spacetime. He saw his work as a final, sophisticated patch on the edifice of classical physics, not as its demolition notice. It was the work of a consummate architect, shoring up a grand but failing structure with beams of exquisite mathematical precision. He had derived the very equations that would become the engine of special relativity, but he could not bring himself to take the final, logical step, to discard the ether entirely and accept that his transformations described the true, fundamental nature of space and time itself. That revolutionary leap would require a different kind of mind, one less concerned with saving the old architecture, and more willing to build a new foundation from the ground up. Lorentz had provided the blueprint. It would take an unknown patent clerk to see that the blueprint was for an entirely new universe. The year is 1905. In the world of physics, the atmosphere is one of profound unease. The magnificent clockwork universe of Newton and Maxwell is showing deep cracks. The luminiferous ether, its cornerstone, is a ghost that must exist yet stubbornly refuses to be seen. The Michelson-Morley experiment hangs over the discipline like a specter, its null result an unanswered riddle. Great minds like Lorentz and Poincaré are circling the solution, adding complex patch upon patch to the old structure, trying to save the ether with concepts of contraction, local time, and hidden conspiracy. The air is thick with complication. Into this intellectual crisis steps a most unlikely revolutionary, a 26-year-old patent clerk in Bern, Switzerland, named Albert Einstein. Einstein was an outsider in every sense. He was not a professor at a prestigious university. He was a technical expert, third class at the Swiss Patent Office. His job was to evaluate the practical merits of inventions, a task that honed his ability to discern fundamental principles from cluttered details. Free from the pressures of academic tradition and the weight of established dogma, he possessed a mind of unparalleled independence and a deep-seated faith in the harmony of nature's laws. While the physics establishment was trying to fix the ether, Einstein was willing to do the unthinkable, to let it go. His thought process did not begin with the Michelson-Morley experiment, though he was aware of its result. It began with a simple, almost childlike question he had asked himself since he was 16. What would a beam of light look like if you could catch up to it? According to Newtonian mechanics, it should appear as a stationary wave. But according to Maxwell's equations, which he revered, light was an electromagnetic wave that always propagated at speed, c-nunc, regardless of the source. Both could not be true. This paradox pointed to a deep conflict between the mechanics of Galileo and Newton and the electromagnetism of Maxwell, while Lorentz and others sought to modify matter and its interaction with the ether to resolve this. Einstein took a more radical axiomatic approach. He decided to start from scratch with two simple, bold postulates that he elevated to fundamental principles of the universe. He was not interested in why the speed of light was constant. He accepted that it was, and he was determined to discover the consequences. This was a profound shift in methodology, from saving appearances to deriving reality from first principles. His environment was crucial. The patent office was his worldly monastery, a place of intellectual freedom. He had a close-knit circle of friends with whom he passionately debated philosophy and physics, most notably the informal Olympia Academy with Maurice Solavine and Conrad Habicht. It was in this fertile ground, away from the orthodoxies of the academy, that his heretical ideas could germinate and grow without being prematurely pruned. In the miracle year of 1905, his Annus Mirabilis, he published 4 papers that would change the world. The third of these, on the electrodynamics of moving bodies, contained his theory of special relativity. In it, he did not mention the ether at all in the introduction. He began instead with the observed asymmetries in the treatment of moving magnets and conductors, pointing out a lack of simplicity in the current theory. Then he laid down his 2 postulates, which were like intellectual dynamite. The principle of relativity. The laws of physics are the same in all inertial frames of reference, i.e., frames moving at constant velocity relative to each other. There is no privileged state of absolute rest. The constancy of the speed of light. The speed of light in a vacuum is the same for all observers, regardless of the motion of the light source or the observer. With these 2 statements, the ether was not disproven. It was made superfluous. It was an idea that had simply become unnecessary. If there is no absolute rest frame, then the very concept of a stationary ether is meaningless. If the speed of light is constant for everyone, then there is no ether wind to measure. The great null result of Michelson and Morley was not a puzzle to be solved. It was the expected outcome. Einstein then proceeded to derive from pure thought and his 2 postulates the same mathematical transformations that Lorentz had painstakingly developed to save the ether. But the meaning was utterly transformed. In Einstein's hands, the Lorentz transformations were not a mathematical trick to explain away experimental results. They were a revelation about the true nature of space and time. Length contraction and time dilation were not illusory effects caused by motion through a medium. They were real physical consequences of the fundamental structure of a universe where the speed of light is the ultimate speed limit. The patent clerk had done what the great professors could not. He had looked at the same data, the same equations, and seen a deeper truth. By questioning the absolute nature of space and time, concepts so fundamental they were considered beyond reproach, he cleared away the philosophical underbrush and revealed a simpler, more elegant, and far more strange universe. He didn't fix the old clockwork. He revealed it was a shadow of a deeper relativistic reality. The clerk had not just changed physics. He had changed everything. Einstein's revolution was not built on a complex web of new mathematics or arcane experimental data. It was built on 2 deceptively simple statements, 2 principles that, when accepted as fundamental truths, force us to tear down and rebuild our entire conception of reality. These are the postulates of special relativity, and their elegant simplicity belies their earth-shattering implications. The first postulate is the principle of relativity. It states, the laws of physics are the same in all inertial frames of reference. At first glance, this seems almost obvious, a refinement of ideas dating back to Galileo. An inertial frame is simply a state of constant, unchanging motion, being at rest or moving in a straight line at a constant speed. Imagine you are in a windowless, smoothly moving train. Could you perform any experiment, dropping a ball, observing the swing of a pendulum, studying the flow of electricity, to determine whether the train is moving at 50 mph or is stationary? The principle of relativity says no. All your experiments will yield the exact same results as they would on the stationary platform. There is no experiment that can detect a state of absolute uniform motion. Motion is always relative to something else. This principle dethrones the ether. If the laws of physics are the same for everyone in uniform motion, then there can be no single privileged frame of absolute rest. The ether, as an absolute rest frame, becomes a meaningless concept. An observer at rest in the ether and an observer moving through it at a constant velocity would both find that Maxwell's equations for electromagnetism and Newton's laws of mechanics hold perfectly true in their own labs. There is no correct perspective. The universe is fundamentally democratic. The second postulate is the one that breaks our intuition. It is the constancy of the speed of light. It states, the speed of light in a vacuum C is the same for all observers, regardless of the motion of the light source or the observer. This is where Einstein parts ways with all classical thought. Let's return to the train. If you throw a ball forward on a moving train, its speed, from the perspective of someone on the platform, is the speed of the ball relative to the train plus the speed of the train. This is simple Galilean velocity addition. It works for balls, sound waves, and anything else. But now imagine you turn on a flashlight on that train pointing forward. According to classical physics, the person on the platform should measure the light speed as cla, the speed of light, plus the speed of the train. Einstein's second postulate says this is wrong. The person on the platform will measure the light speed as exactly c. The person on the train will also measure it as exactly dangamar. It does not matter that the source of the light is moving. The speed of light is a universal constant, a fundamental speed limit of the cosmos that cannot be exceeded or added to. This creates an apparent paradox that shatters our classical notions of space and time. How can two observers moving relative to each other both measure the same beam of light to be moving at the same speed? The only way to resolve this paradox is to accept that the measurements of space and time themselves are not absolute. They are relative. The very fabric of the universe must be flexible to accommodate this unyielding speed of light. If the speed of light is fixed, then something else must give. That something else is our universal common sense understanding of space and time. To make the speed of light constant for everyone, the universe adjusts the measurements of moving observers. Specifically, time dilation. A moving clock ticks more slowly relative to a stationary one. Time itself stretches and slows down for the moving observer. Length contraction. An object in motion is measured to be shorter in its direction of motion relative to a stationary observer. These are not illusions or mechanical effects. They are real physical consequences of the universe's structure, forced upon us by the two postulates. The mathematics that describe these effects are precisely the Lorentz transformations, which Einstein now derived not as a fix for the ether, but as a direct consequence of the fundamental nature of space and time. Together, these two postulates form the unshakable foundation of special relativity. The first postulate establishes the democracy of all inertial observers. The second postulate provides the universal non-negotiable law that governs them all, the cosmic speed limit. To obey both, the universe must be one where space and time are woven into a single, flexible fabric called spacetime, where simultaneity is relative, and where our everyday experience is merely a slow-speed approximation of a much stranger and more wonderful reality. Einstein took two simple ideas and followed them to their logical, mind-bending conclusion, forever changing our place in the cosmos. With the publication of Einstein's 1905 paper, the luminiferous ether did not simply fade from view. It was issued a formal and logical death certificate. Einstein's theory of special relativity did not disprove the ether through a new experiment or by finding an error in the old mathematics. Instead, it rendered the entire concept superfluous, a solution in search of a problem that no longer existed. The ether was not defeated in battle. It was made redundant by a radical new understanding of the universe's rules. The core of this obituary lies in the fundamental shift from a dynamical to a geometrical view of reality. For physicists like Lorentz and Fitzgerald, the ether was a physical substance, a thing that could exert forces and be moved. The null result of the Michelson-Morley experiment was a puzzle that required a dynamical explanation. Matter must change its shape, contract, and its timekeeping, slow down, as it plowed through this resistive medium. Their transformations were a brilliant, complex description of how matter interacted with the ether. Einstein's genius was to realize that the Lorentz transformations were not about the properties of matter, but about the properties of space and time itself. He eliminated the ether by eliminating the need for an absolute state of rest. In his universe, there is no at rest. There is only at rest relative to something else. The very question the ether was designed to answer, what is the medium of light relative to, was revealed to be a meaningless question. It was like asking what direction is true north on the surface of a perfect sphere. Every point is just as valid as any other. This becomes clear when we revisit the central puzzle, the constancy of the speed of light. In the ether model, this constancy was only true for one privileged observer at rest in the ether. For everyone else, the speed of light would vary, just as the speed of sound does for a moving observer. The entire purpose of the Michelson-Morley experiment was to detect these variations, to find our velocity relative to this absolute frame. Einstein's second postulate demolished this entire line of inquiry. By declaring the speed of light invariant for all inertial observers, he made the concept of an ether wind a logical impossibility. If the speed of light is always measured to be co, regardless of your motion, then there is no wind to detect. The great null result was no longer an anomaly to be explained away with contractions and dragged mediums. It was the expected default state of the universe. The experiment wasn't a failure. It was a precise measurement of a fundamental principle. Furthermore, Einstein's first postulate, the principle of relativity, stripped the ether of its last remaining function. The ether's primary role was to be the medium that transmitted electric and magnetic forces, the stage for Maxwell's equations. But Einstein's theory showed that Maxwell's equations already satisfy the principle of relativity. They work perfectly, and take the same form in every frame of reference without needing to be anchored to a stationary medium. The ether, which was meant to be the foundation for electromagnetism, was like a scaffolding that was left in place after the building was complete, not only unnecessary but actively obscuring the elegant structure of the building itself. The death of the ether was therefore a profound instance of Occam's razor. The ether theory had become bloated and complex, requiring a substance with impossible properties, infinitely rigid yet massless and frictionless, and a host of ad hoc explanations, contraction, local time, to remain consistent with experiment. Einstein's theory achieved the same explanatory power, and far more, with a simpler foundation. Two clear postulates about the laws of physics and the nature of light. The ghost was exorcised not by a more powerful ghost, but by the realization that there had never been a haunted house to begin with. The ether's obituary is not a story of failure, but one of necessary evolution. It was a vital, productive concept that guided physics for a century, pushing it to ever greater experimental precision and theoretical refinement. Its ultimate demise was its greatest gift, for in trying to save it, physicists like Lorentz and Fitzgerald had inadvertently derived the very mathematics that would make it obsolete. They had built the coffin for their own most cherished idea. Einstein simply had the clarity and courage to lay the concept to rest, clearing the way for a universe that was stranger, more beautiful, and far more democratic than the one governed by an invisible absolute medium. The void was not filled with a substance. It was revealed to be a dynamic, flexible geometry, a stage that was also part of the play.